So now we move on to current calculations. Okay, we're slowly learning what Ohm's law gives us and how we can use Ohm's law and the three different configurations of the expression to solve for voltage, current, and resistance. So in this example, how many amperes of current are in the circuit? Okay, so if you look at the circuit, we can see we've got 100 volts at the source. We've got a fixed 22 k ohm resistor, and we have an unknown current here. So if we use the formula, current is equal to voltage divided by resistance, and we substitute 100 volts for V and 22 k ohms for R, we can come up then with the value of 4.55 milliamps. Okay, so very simple. You just substitute the values in, and you solve for the unknown. We're going to see as we go on, the problems are going to become more complex, where you're going to have to do some conversions and some manipulations to come to these solutions, but it's a process. You just keep working on it. Again, I hope you're keeping a notebook handy and you're writing out these problems and making notes to yourself and little drawings on how to solve these types of problems. So they give you a related problem. Again, work this one out for yourself in your notebook and learn how to make these types of analysis. If the resistance then in the previous figure is changed to 47 ohms and the voltage to 50 volts, what is the new value of the current? So the solution says we substitute 50 volts for V, we substitute 27 ohms for R, and now we come up with a smaller current of 1.06 amps. Okay, so solving for current using two of the known values. Go ahead and work the related problem. Stop the video here, pull out your paper, work the related problem of 5 volts and 1,000 ohms. Again, get used to taking that 1,000 ohms and converting it either to 1 k ohm or 10 to the third ohms. Okay, getting used to this engineering and metric notation. All right. Okay. So we've got our little values there. Units with metric prefixes. Okay, this is what I keep harping on you to make sure you start using and understanding the metric prefixes and how we go back and forth from metrics to exponents to full values. In electronics, resistance values are thousands of ohms or even millions of ohms and are commonplace. Okay, very rarely will you see values down at the 1 ohm or something like that. You're going to see things in the mega ohm or in the k ohm region. The metric prefix kilo, K, and mega, capital M, are used to indicate large values. On these values here, don't confuse little m and big M. Little m is milli, which is 1,000th, where big M is mega, 1 million. Thus, thousands of ohms are expressed in k ohms, and millions of ohms are expressed in mega ohms. The following 4 examples illustrate how to use k ohms, kilo ohms, and mega ohms to calculate current. Volts divided by k ohms results in milliamps of current. Okay, and if you just look at it, we can see that we've got those inverse relationships that lead us to a milliamp of current. Volts divided by meg ohms give us microamperes, or 10 to the minus 6th. So if we look at the simple circuit again, 50 volts, 1 k ohm, unknown current. Remember that 1 k ohm is the same as 1 times 10 to the third ohms. Use the formula I equals V over R and substitute 50 volts for V and 1 times 10 to the third ohms for resistance. So when we make the substitutions here, You can see we did that here, 50 volts, 1 times 10 to the third. We can see that all we really have to do is take the 10 to the third, move it into the numerator, change the sign of the exponent to a minus 3, and we have 50 times 10 to the minus third, which is 50 milliamps. If you wanted to express this without the milli, it would be a matter of moving the decimal point 1, 2, 3. So it would be 0.05 amps, okay, rather than milliamps. Okay. How many milliamps are in the circuit of 3.8? So again, the simple circuit, 30 volts, 5.6 times 10 to the third, or 5.6 k ohms. We take the values, we put them into our relationship, V over R, and we end up with 5.36 milliamps of current. Again, when you're working these problems, make sure that you are adhering to the significant figures. Some of you are going to say, well, that number that I just gave you is the number that was on the calculator. That is not the answer. The answer is when you look at the calculator and determine by the significant figures what the correct answer should be. Okay? So, take a look at the related problem and solve for the unknown. Determine the amount of current in the circuit. Again, 25 volts, 4.7 meg ohms. Okay, we substitute our values, 25 volts, 4.7 times 10 to the 6th. We move 10 to the 6th into the numerator. 4.7 divides into 25, 5.32. And now we have 5.32 micro amps, 10 to the minus third amps. So we are more and more we're using these metric values and our exponentials to help us solve the problem. If we change the value of R in the circuit to 1.8 mega ohms, what is the new value of the current? So again, leave the voltage at 25 volts, 1.8 mega ohms, we get 13.9 microamps. Small voltages, usually less than 50 volts, are common in semiconductor circuits, which we're going to see in later courses. Occasionally, however, large voltages are encountered. For example, a high voltage supply in some television receivers is around 20,000 volts, or 20 kV, 20 kilovolts. And transmission voltages generated by power companies may be as high as 345,000 volts, or 345 kV. So if we take our relationship here that we've done in the past, and we look at the same relationship with the current, we can solve for, again, unknown currents. How much current is produced by a voltage of 24,000 volts across a 12,000 ohm resistor? Okay, if we look at this problem as it's set up, we have 24 kV, we have 12 k ohms, and that relates to exponentially 24 times 10 to the third, 12 times 10 to the third. You see cancellation occurring here? 10 to the third over 10 to the third cancels. K over K cancels. So we very simply, by inspection, can see that what we're going to have here, 12 divided into 24, is 2 amps. Okay, if we look at the next problem here, we've got a 100 meg ohm resistor and a 50,000 volt source. So again, as we plug our numbers into the relationship, 50 times 10 to the third, 100 times 10 to the sixth, we can see that we can move the exponents around in the numerator and denominator. When I move 10 to the sixth into the numerator, that becomes 10 to the minus 6 and 10 to the third, which leaves 10 to the minus third. And 100 into 50 is 1/2, or 0.5. So we need to start to learn how we do these relationships where we start moving our exponents and our metrics around. Okay, so we'll stop there.